which I've been forgetting each week. And let's go to, where's my, where is, there it is, okay. So hopefully you can see a paper that I wrote called Information Theory on Claude Shannon. Does everybody see that?
Yes.
Yep.
Yeah.
Great. Okay. So this was, as I said, originally just going to be additional information, but it's turned into being this week's presentation. All right. So we're going to have a couple of topics. We're going to go back to probability and our old friend, the alphabet, a couple of distributions, the zip distribution, and something called digrams and trigrams, etc., all used for making a discrete Markov process. And that's basically what I had for a addition. Okay. All right. So now, okay. So you've seen this picture before. This is our information source. There's a selection from the information source that has a message. Each of those messages in the information source has a probability associated with it. There's a transmission of that message. The transmitter is usually some type of a way to transform the information source message into a signal that can be sent over some kind of a channel to a receiver. The channel itself has noise. There can also be noise in the transmitter and in the receiver. So at the receiver end, the signal is received and translated, and if it were perfect, it would do the inverse of what was done at the transmitter, and the received message would be identical, and that is handed off to the observer who's the destination. In our Alice and Bob story, Alice selects the message. We've been talking about it as a couple of different things. One as just a yes/no bit, and second as an alphabet. And the particular sequence of, if we do use the sequence of symbols, the assumption in the design of information theory and communication is that the sequence of symbols that come down the channel are known as a stochastic process. So given a letter as an initial condition, the next letter is another random signal that comes down. Now, that doesn't sound like it would work very well for making messages, but we're going to do an example here to show how they can work. And this is Shannon's figure number 1, the one that he used for designing the communications theory. Okay. there's an article on the on stochastic problems in physics and astronomy by Chandra Shekhar, which is a good reference. Okay. So, as I've said several times, probability is observer dependent. So I'll try to be a little bit more accurate in the symbology that I use to represent compared to what I have done in the past. Let's consider our Alice as the message sender and Bob as the destination. The location is a noisy party. The channel is Alice's voice transmitted from her mouth via the air to Bob's ear. The question that Bob asked, Alice, required an answer from a source, that is the collection of messages, S, that were to be transmitted are either A or B. I'm sorry, the source has been agreed on by Alice and Bob. So the collection of sources have been agreed. And in this case, S is either yes or no. And as I said, the source comment's been agreed on by both Alice and Bob. But Bob has complete uncertainty about what the answer is. That's the reason that he asked Alice for the question. And his probability is, of course, 0.5 and 0.5 because he's completely ignorant. So we're going to use a different symbol. The E of P represents the experience of the person. And this is the more, the table up there is Bob's a priori probabilities for the possible answers. So I would, if I hadn't had a table caption, I would have used in the probability given Bob's E of B, Bob's experience. So Bayesian probability is always conditional. The a priori marginal probability density of sources given Bob's experience. So we have the collection of messages S given Bob's experience, and that is denoted as a probability. And this gets more complicated, but hopefully you can understand what is being said. So for each probability of the source, S sub j, where j is whatever, I'm sorry, I have the j in one place and a k in another. Oh, well, yeah. So the probability given Bob's prior experience is given by a sum of numbers, the probabilities P sub I times the Kronecker delta of I and j. So the Kronecker delta is very similar to the Dirac delta. The Dirac delta is the continuous version of the Kronecker delta. And each of the SJs are in the collection of sources. So if J is equal, say, to 1 for yes, then summing over this, I and only the 1 will be a 1, the rest will be 0. So you'll wind up with p sub 1. So p of s sub j is p sub j, is the result of this computation. Is all of that fairly clear? I'm trying to be more precise than I have in the past.
Now, for your example of a yes and no, I would be sum from 1 to 2? Or
Yep.
are we?
N would be 2. The S sub k's would be yes and no. And if you had P of yes, then I would go from 1 when J would be 1. And when you summed over this, 1 and J, since J is 1, would only, the P1 would only be the one coming out here. If you had J equals 2, then the same thing works, but now J is 2, so the only one where the Kronecker delta turns out to be 1 is the 2, so you get P sub 2. Is that all fairly clear?
Is it the right-hand side always just P sub j?
Yeah.
Okay.
That's exactly what that's what the thing shows, yes. But if you don't know what J is, this is the general result. And okay, so yeah. So B's a priori probabilities, in this case, for the input source, the input source has Alice's source messages coming in, but they're agreed upon here. Alice and Bob have agreed upon what the source is, and for all K, they're identical. So Bob's output source system is identical. Now, Bob's a priori probabilities are half-half. So Bob's entropy is the entropy of the source input for Bob, given Bob's prior experience, which is, I think I have another paren in here, I apologize. Anyway, it's equal to 1/2 log 2 of 1/2 plus 1/2. This is P and 1 minus P, since they're 1/2 and 1/2, which is 1 bit. So the channel with noise uses a joint distribution. So the channel has and we're talking about a symmetric channel right now. And okay, so the joint probability is the probability of S sub I and S sub J. So this is a table of 4 probabilities in here, where the S in is the original signals and Sj is the outs. So the symmetric channel means that Sin equals S out, and the error probabilities are also 0. If you can see on the, we've used this figure before. So this is our sources of Alice, and I'm sorry, I've got my gallery over that. That's not going to work here. Where am I going to move it?
We see that.
Okay, let's move this.
Our gallery isn't muting or isn't covering that. Yours might be.
Mine is. That's why I had to move it. I apologize. All right. So here is the symmetric channel. The probability that there is a flip, a 0 goes to 1 or a 1 goes to 0, is in both cases the same probability, namely E. The probability that it goes from A to B, it doesn't flip, gives you the correct answer, is 1 minus E in both cases. That's the symmetry. And the symmetry is both the sources are identical and the probabilities are all identical. Okay. So A's experience has to be different from Bob's, or why would he bother to ask her a question? If she didn't know or have a pretty good answer of what the probability is, she'd be a pretty useless person to give you an answer. So I'm making an assumption here that she knows at least 98% probability. So her entropy is quite different from Bob's. Okay. Whoops, sorry, that wasn't supposed to happen. Hello? What am I doing wrong?
You're going forwards instead of backwards.
I know that the question is why.
Well, why? Okay.
Okay, here we go. I've not used the arrows on my keyboard very much. Okay, so we've talked about this and we've talked about the symmetric structure of it. So B's symmetric probability joint probabilities are given by the source input of yes and the source output of yes is 1/2 1 minus E, and source output of no is 1/2 E, and it's symmetric. So the P21 is 1/2 E, and the P22 is also 1/2 1 minus E. So, but come on, I'm not used to working with this kind of a structure. Okay, so if you use the formulas for the probabilities that we showed before, and we write out the joint entropy, which is just the sum over I 1 to 2, sum over j 1 to 2, Pij log 2 Pij. This is 1 plus what I'm calling entropy of E.
Bob, could you tell me again where that 1/2 comes from?
Well, our marginals always in both directions have to be the same as the probabilities. This is all from Bob's point of view. So his input source is 1/2 1/2. His output has to be 1/2 1/2. So if you sum this way, you get a half. And if you sum this way, you get a half.
So the input source, that's where I guess my question lies. The input source, 1/2 and 1/2, that means
Yeah, this is all Bob's point of view. This is the
okay.
information that Bob knows about.
Okay.
The reason he's asked Alice a question is because she has a different set of input probabilities.
Okay, so this is before the question is asked.
Well, before it's answered.
Before it's answered. Okay.
Right.
Good.
Okay.
Then I understand.
Is everybody clear about this? Okay. So now the h of e is e log 2e plus 1 minus e log 2 of e. And I suggest that you do compute that joint entropy that I had in the previous table as an exercise. And this is a picture, which I don't know how well it's going to blow up. It won't go any more than this, sorry. Okay, so the two components, e log 2e, are, let's see, it is this one, the dark green one. The 1 minus e log 2, 1e, 1 minus e is the light one here. And the sum of those two, which is h of e, is this. And it's symmetric. And it's versus the probability e going between 0 and 1. And it has a maximum at 0.5 at 1 bit. So we had said previously that the joint probability was 1 plus h of e, and because of Bob's ignorance initially, it is 1/2, 1/2. So the total joint probability is 2 bits in here. Everybody follow that?
Yeah.
Okay. This has been. I'm just trying to be a little bit more.
I'd like to ask something.
Sure.
Okay, you've laid out the probabilities of the transmission arriving at the receiver correctly or incorrectly. And what I'm wondering is, how does the receiver know which of those two possibilities it is?
Well, he doesn't. That's the reason he asked the question.
Okay, but when he gets the answer, again, you have the probability of it could be right or it could be wrong.
That's correct. And
so, okay.
That's why, because you can have errors in the transmission, we're next week going to talk about error correcting codes. Codes, we've talked about codes in terms of like the Baudot or ASCII 5-bit codes, and those had enough information to carry the signal of an alphabet exactly. But if there was a bit that had an error in there, you'd get a different letter out. So we're going to be able to understand that by using more bits in the signal that you send, you can discover by carefully designing the code how you have discovered which bit was an error. And you can then go back and correct it. Because they're with an extra bit in there, actually you need 3 bits in order to correct it. But if you have 3 bits instead of 1, then every 1-bit error can be corrected because there's only 2 possibilities out, but 8 possibilities sent. So by knowing which one of the bits came, you can find out what was the signal if there was only 1 bit of error. But we'll get to that next week. I'm not going to get to it here. Is that answering your question?
Yes, it is. Thank you.
Okay, good. Okay, so So that was the what we were talking about last time about H of B and where all the probabilities came from and stuff. And we had a conversation about it at the end of the lecture last week. So I thought we needed to go over that in a little bit more detail. I apologize for all those symbols, but in order to be completely accurate, I needed to use this complicated symbols. So if you remember our alphabetic, our 5-bit description of alphabetic characters, like the Buto or the ASCII, we used our probability, our assumption of the postulate of a priori equal probability. So how useful is that kind of a system? That is, all letters are equally independent and they're all equally likely. Well, if you take a random set of letters and you also assume that there's an equal probability of 1, 2, 3, 4, or 5 character words, then if you run that, you get this kind of a paragraph, which doesn't look like English at all, not surprisingly. So that tends to say that the assumption that we were making originally was a pretty poor assumption. So we're going to talk about various kinds of structures that exist in the English language. So
There are only 3 real words in that paragraph. So
yeah, well,
there's 2 I's and an A. The rest of them, there's no words.
right. Like I said, it's a pretty bad assumption as far as I'm concerned.
Does this relate to the monkeys typing Shakespeare on how many monkeys would it take? How long to type
Exactly.
Shakespeare?
Exactly. This is it. Okay, so it doesn't look anything like English. The formation of English sentences is a highly structured and history-dependent process. The probability of using specific words in a sentence strongly depends on the history of the word usage earlier in the sentence. And I'm going to start with just the alphabetic, character structure in English language. In order to get there, I'm going to have to talk about the zip distribution. Zip is actually a person, and all of these distributions are usually eponymous. That is, the zip distribution was designed by Zip. The Gaussian distribution was designed by Gauss, and etc. Anyway, for many of the distributions, that's the way they came from. So letter frequency, let's see. Yeah. Okay. So you can look at word lists by frequency grouped within any given corpus. A corpus is a collection of text from various sources. And they can either be a ranked list, or they can have the purpose of vocabulary acquisition, all kinds of reasons for wanting to do that. And the nation said a word list by frequency provides a rational basis for making sure that learners get the best return for their vocabulary learning effort. Sorry. So what you're saying is if you're going to be teaching words to people in the English language, the words you ought to be choosing are not random, but ranked by the order of frequency in the English language. Frequency lists are also made for lexicographical purposes and make a checklist to ensure that words are not left out, things like that. The major pitfall is the corpus content. So the corpus is the collection of text that is used as a source. And for instance, various kinds of studies have been done on Moby Dick, but that's a pretty, although it's a big book, it's not completely representative of the natural language of English. So most of the results that you get are corpus dependent. So that you just need to be aware of that. Okay, so George Kingsley Zip, who was from 1902 to 1950, he was an American linguist and philologist, like Tolkien, who studied statistical occurrences in different languages. The picture on the left here is George's high school graduation picture. It's the one that is used in Wikipedia, so that's where I got that from. And it is a relatively straightforward description in the probability of each letter or word, whatever, depends upon a single parameter row. And in his original description, he just had row equals 0. It was later generalized in here. And the zeta function, also known as the harmonic number function, is the sum from 1 to the number of characters you're talking about, divided by 1 times n to the s power. So here, so this is the sum of k to the minus rho minus 1 divided by this, where s is rho plus 1. So this normalizes the probabilities, and this is good for 1 to m, and it actually even works if m goes to infinity. So this is the zip law, and many, many studies have been done and shown that zip distributions are just all over the place on various languages, on all kinds of economic results. There's just a tremendous amount of work on the zip distribution in many different, beyond linguists here. Okay, so the normal, if in the original design, rho was 0, and that meant that if the Actually, it's supposed to say 0. I apologize. This means that the second item will occur 1/2 as often as the first, and the third one 1/3 as often as the first, and so on. Each one drops off as relative to the first one. And if rho is nearer to 1, not 2, I'm actually talking about rho plus 1 in both cases here. I apologize. This type. ZIPS was one of the first academic studies on word frequency. So let's take a look at Hamlet. I've got a copy of Hamlet, Gettysburg Address, Alice in Wonderland, and the Federalist 10. And I found all frequencies of a space and letters A to Z after making them all lowercase. And the result, this is the counts here, the total number of characters in the sample, in the corpus, was 230,000 characters. And this shows the bar chart. And obviously the one that occurs the most is the one that has no letter behind it. That's because it's the space. Spaces are the most frequent things to occur in English. The next one is the one we expect, E, and then T, O, A, etc., down to Z. Now, you can see this sort of drops about 1/2, but this is not about 1/3. That would be a little further lower, and this is not 1/4, etc. So obviously a non-zero value of rho needs to be approximated. I didn't use a completely Bayesian updating to get the approximation that I did. Instead, I used a maximum entropy approximation to the zip distribution. It turns out if you use the regular statistical process, which is to take the log and get the slope, you get all kinds of weird answers. And if you use even maximum likelihood estimates, they're all over the map as well. However, for the maximum entropy is the most uniform approximation that you can use. It is if you do the same set of results sampling from a particular distribution repeatedly, and you look at all the results, rather than going all over the map, they're always very close. So that was the reason I used the maximum entropy approximation. And okay, so here is the log-log plot of the Hamlet et al. Corpus. So the number of letters is 230,000, and the purple dots are the empirical frequencies of each of the letters that I showed in the previous one. And the approximation, 1 plus rho was 2.043. And the orange dots are the results of the zip distribution of these probabilities in the same log-log structure. So you can see that they're actually not too bad. They're pretty accurate.
What is the abscissa? I'm not quite clear about that.
These are 1 through n log. So we go from 1 to 2 to 5 to 10 to 20 to 27. Because there's only 27 characters in the corpus. A through Z in space.
Right. Okay.
So this is 1 to 27, and these are the logs of the probabilities, or in the other case, the empirical frequencies. And this is the reason most people use a straight line approximation is because of the fact that whenever you take a zip distribution and you plot it in a log-log form, it turns out to be a straight line. But the results that you get using either least squares or maximum likelihood just aren't very good, aren't very consistent, whereas the maximum entropy methodology gives you a consistent set of results.
So you're plotting letters of the alphabet from least frequently used to most frequently used in the abscissa.
Right. So Z up here, and then E in space up here.
Gotcha. Okay.
Okay.
Yeah.
And the numbers from 1 to 27 correspond to the order in which I showed in the previous, let's see. Whoops.
Yeah. I see.
Okay. Oh,
So the orange zip line, would be the same for all works, not just Hamlet. Is that right?
well, this is Hamlet and Gettysburg Address and Alice in Wonderland and the Federalist 10. So when I say et al., I mean that the corpus here was not just Hamlet, but Hamlet, the Gettysburg Address, Alice in Wonderland, and Federalist 10.
Okay, that clarifies that. However, to expand my question, what I'm saying is, why should the zip line be different for anything that you plot? The purple line, of course, would be different depending on the individual work, but the zip line hypothetically should be the same.
Well, it hypothetically should be, but how do you know what it is? Except by taking a look at samples from the English.
So if you use a different corpus, then you would fit a zip line to that, and that would
Have a different
row.
slope, right?
Yeah. Okay.
So you don't know a priori what that slope is for all of English. All you can do is take samples, and if I have some time this week, I'll get all of the Wikipedia text and get that in, and I think that's several million characters, and I'll get the result for that and compare it to what we had here.
What
But-
about if you took the frequency of the letters in a regular Scrabble game? Does it follow one of these? I mean, going the other way around, if you wanted to give somebody a group of letters that they could build, you know, all the words or something like that. I wonder if these gamers, the word games, as particularly Scrabble, what its line would look like.
Well, when you're looking at Scrabble, you're looking for words that have all these high letter, the numbers in the letters are sort of proportional to this. That is, E is a low number, and Z and Q are high numbers.
No, I was meant just how much when you buy a Scrabble game, when you have your Scrabble game, if you did this, got the zip line parameter for the Scrabble game. It would be interesting to see if that's the way you were given letters to use.
Yeah, I've never studied it. I don't know, and I don't know of anybody who has.
Well,
So,
I think in Scrabble, you're limited to from 1 to 10 as far
yeah,
as far as valuation is concerned, or 1 to 9. I can't remember.
No, I don't mean value. I meant if you take your Scrabble box and you count how many E's you have, how many T's you have, how many O's you have, how many A's, would it follow as if distribution?
I don't know. So I
got a Scrabble game. I'll see if I can get that data.
okay, great.
And of course, in Scrabble, you don't have a space. So you
Right.
have to eliminate
You got a
that.
lot of spaces.
Well,
You got the whole board.
Okay. Yes.
that's another question.
Okay. Well, you can eliminate spaces and just look at the letters, and they also turn out to be very similar. So we could look at that just on that point of view. Okay. So using this zip distribution, I now did a completely random collection. That is, I had no a priori probabilities on the number of characters in the, I just chose 1 through 27, converted that into a character, and what do you get? This is what you get when you do that. So obviously, a lot of the structure, just having spaces in it, you don't have to guess on the number of letters in the word, although we will do that later. We'll do it a different way. Sorry, that's not accurate. I take that back. Okay, so this still doesn't look all that much like English. There's an awful lot of E's and O's and things that surprise you, but I don't think there's a few words in here, but not many. So it's still surely not English words, but it seems to feel better than the completely equally likely random letters, at least to me. And notice there's no assumption about word sizes in this. This was just made by choosing the space from the zip distribution. So the fact that there's a space character in the part of the distribution means the word selections are reasonably correct for English language without needing to add that additional assumption. Diagrams. All right. So the next thing you can do is make a more complicated structure. So you can make successive symbols not chosen independently, but the probabilities depend on the preceding letter. So in the simplest case of this, a choice is simply to take the preceding letter and all of the ones that are after it and do the frequencies on those. Those are a set of transition probabilities, P for each letter I, the starting letter. There is a probability for all of the other letters J in the symbol set. And in this case, when I do the calculations, it'll again be in our Hamilton et al. Group of English. So the probability that any letter I is followed by a letter J is this piece of I of each of the J. And of course, both I and J range over all the possible symbols. And a second equivalent way of doing this is to just write them as instead of a set of lists, you can write them as a matrix. So you have a probability of I and J. And these are each of the relative frequencies of the diagram for I and J. By the way, did I mention that two symbols together are called a diagram, three are called a trigram, and they go up from there, as many as you want to do. Okay, so if you have the piece of I times J, you also need to know the probability of the I's in order to get a piece of IJ. And so in the way we've been designing it here, if I've got the list of corresponding probabilities given each I, and I use the probability of each of the initial letters being the zip distribution, then Pij would be the multiplication of the two in here. So knowing these and knowing these, you can compute these. Okay. So these are called, piece of I of J are called transition probability. We're going to be talking about a mathematical model that describes building words that are called discrete Markov processes. And so the initial probabilities will be from the zip distribution, and all of the transition probabilities, that is from A to all of the others, are from another set of collections. Okay. These, yeah.
Quick question. The chart you showed us before, the graph of the data for the 200,000 letters in Hamlet, etc., and this grid here, those are statistics, right? They're not probabilities, they're statistics. And I don't mean to be semantic, you know.
I apologize, my voice, hearing you just went out. So could you please repeat the question?
Sure, I'm sorry. Like this grid here and the couple previous graphs you showed us indicating the results for these samplings of letters. These are really statistics versus probabilities.
Correct.
Okay, all right.
But you know, you would, to do it properly, and I didn't do a complete, you would have to know a prior probability on what each of the various things that I were doing. And could you please cut whoever is talking about that? So you would need to know the prior probabilities on all of these, and if you were completely ignorant, you would just make them all uniform, but we all know they're not, so you'd have to choose something else, and it would depend upon what your choice of that was, and then you have to do Bayes' rule for every character that comes up, add it into the distribution, and you'll eventually get a set of probabilities out.
Right, okay.
Now, I didn't do that because A, it's a heck of a lot of work, and B, it would depend upon what I chose for the initial probability distribution. So you might not like it. You might want a different one. So I just used an approximation here.
Okay, thank you.
Okay. So, okay. So I found the joint probabilities for 2 letters, 3 letters, and the 2-letter probabilities here are shown in this picture. A graph, I mean, a 27 by 27 matrix of numbers doesn't communicate very much to me. But these give you more feeling. So V followed by, V followed by E is one of the most frequent things to occur. Q followed by, oh, come on, get out of my way. Yeah. God. All right, let's put you over there. So another one is Q followed by U. And as you know, if you, in fact, it looks like that's the only 2-letter diagram for Q. The rest of it looks to be, well, there's a little bit of things here. So, okay, it's not completely QU, but QU is clearly the most frequent occurrence. So the dark ones are the ones that are very frequent. The gray ones are in between. They're somewhere between, say, about 0.4 and 0.6, and the lower shades are between 0.2 and 0.4, and then the other ones that are very light are between 0 and 0.1. So this is the, and again, this is empirical, not any kind of a model, but you can, so you can use the zip distribution that I did before, and then you can follow and get a second letter by using this. Then after you've got 2 letters, you can go to trigrams. This is a diagram, 2-letter probabilities. You can do a letter for, you can do a probability for each letter given all possibles. So you got whatever AA, AB, AC, etc. to ZA, ZB to ZZ. And so the trigrams would have whatever 27 squared is, numbers of probability. One of the problems that you run out with any particular corpus is that you're starting to get numbers that are very large to the total number in the corpus. And obviously, once you get to that point, the resulting statistics are almost useless. So we can also, what this kind of structure is called a Markov process, a discrete Markov process. But the ones that are currently used in most English languages are what are called hierarchy hidden Markov models, as opposed to discrete Markov models. But and the difference is that in a hidden Markov model, there's an assumption that the internal structure is not 1 letter at a time. So in a hidden Markov model, the number of characters that gets structured, that comes out, may be 2, 3, 4, 5, something, rather than 1. And they found that this kind of a structure is better than a discrete one, but we're going to stick with just a a discrete Markov model in the work that I'm doing here. So a second order, again, a typo, I apologize, approximation using just the diagrams and the zip distribution gives you this kind of following text, okay? It certainly looks a little better than anything we did before in here. If you add a trigram on here after a diagram, it gets even closer. This actually begins to look like, you know, just badly mistyped words. And okay, let's see. Okay, now I need to move my gallery out of the way. Okay, so we can also use random words chosen from a dictionary. So if we take a look at a first order that is a zip distribution on words, and now of course they will all be English words because they're all words chosen from a dictionary, but we choose them in proportion to the probability of each word occurring in the dictionary. And if you do that, then you get obviously stuff that are all good words, but the language structure is not real good. So if you now use diagrams on these and you use the zip distribution and the diagrams, you wind up with something that almost looks like English. The head and in frontal attack on an English writer that the character of this, anyway, it almost sounds like English. So if you go to a third approximation, you get even better here. So let's, everybody follow what we're doing?
Yeah.
Okay.
Yeah.
Great. All right. So the resemblance in ordinary English text obviously increases quite noticeably above each step. The samples have reasonably good structure out to about twice the range that is taken into account of their construction. That means that if you have enough samples in the initial zip distribution and the initial diagrams, then a reasonable sequence of letters will be very good. And similarly, if you do it for a word order, 4 or more words, it can be easily placed in sentences without being too particularly strained or constructions. So the sequence of 10 words that came up above, attack on an English writer that this character of this is not, I mean, it's not great English, but it is almost understandable. So it seems that a sufficiently complex stochastic process can give a reasonable satisfactory representation of our discrete source. Not the initial, I mean, we were doing one bit, there's no problem. But when you start doing the alphabet or you start doing words, you need to do more complicated probability structures. And the stochastic processes that I've been talking about are called discrete Markov processes. And they're extensively studied. And I'll show a simplified BMP showing just 3 letters. So this graph, this is what is mathematically known as a graph. The discrete Markov process completely describes the behavior of this BMP over the 3 letters A, B, and C. So if you start with A and you look at it, you have a transition to B of 0.8. And there's also a transition to C of 0.2. You take a look at B, B has a transition to itself with probability 0.5, and the transition back to A also 0.5. For C, we have a transition from C to C, we have it with 0.1, a transition from C to A of 0.5, and I'm sorry, yeah, C to A,
And then C to B.
yeah, I don't know that it goes to B. It's not necessarily supposed to, but
But you get the 1, you get the 0.5, the 0.1, and the 0.4.
right.
They all have to add to 1, right?
Oh, here, okay, C goes to B. Yes, you're right. Okay, good. There it is. I knew it was there somewhere. Okay, so 0.5 plus 0.1 plus 0.5 is 1. Good. So that's how you read the structure of a discrete Markov process. So how does this model work? Okay, obviously the first thing you need to do is an initial condition. So you have to choose some initial character. Then we have the transmission probabilities that we've been talking about. And just for now, let's choose 5 random probabilities between 0 and 1. For example, 0.95, 0.22, 0.48, 0.91, and 0.66. Those are just random probability numbers between 0 and 1, uniformly distributed. So I'm going to start the process with an initial condition of C. Now, the cumulative probabilities are of C, which we had up here. C had a C to itself of 0.1. Then it went to B with 0.4, so that made it 0.5. 0.1 plus 0.4 is 0.5. Then it goes to A with 0.5 to 1. The first random uniform distribution number was 0.95. Since that's between 0.5 and 1, we have our first transition, C goes to A. So C1 is A. So we have 2 letters now, C and A. The next probability is 0.22. We're leaving from A, and the cumulative probabilities of A can go to B with 0.8 probability, and it can go to, what else it goes to? It goes to C with 0.2. So we have 0.8 and 1 going first to B and second to C. So since our 0.22 is less than the 0.8, our transition is again A. So yeah, that's a typo. Okay. So, whoops, what did I do wrong? I went the wrong way. So the resulting letter transitions that we talked about would be A for A goes to B is 0.8, A goes from A to C goes 0.2, and all of these add to 1, and I should have probably typed in the cumulatives as well, 0.81, 0.51, 0.1, 0.5, 1, and at each stage, whoops, that just annoys me. Okay, so we have these probabilities, and you want to finish out the, as an exercise, another exercise, you should see that you understand how all of the resulting letters come out. And in this case, it's CAACC. No B's come out. So this is an example, and you should verify that that's correct. I just did it in my head while I was typing, so I could have made a mistake. Let me know if I did. That's the kind of models that are generally used for describing the structure of sources in channels, if they're English language related. So the zip distribution, diagrams, trigrams, etc., either done on letters or done on words is how it generally works. So this was going to be just a little additional thing I was going to send out, and I was going to put more work together in my slides, but I wound up only doing this week, so we'll have to continue next week. Questions?
Could you go back to how you actually work through this process, this last process, one more time? I've seen some of this before, but these randomly selected probability, that's the probability for each step through the process?
Right. So you choose a random number, and the first one I chose was 0.95. You have an initial condition, so you start at C. You have the table here. C goes to C, 0.1, C goes to B, 0.4, cumulative 0.5, and C goes to A, cumulative 1.
So it's the cumulative distribution. It's where the first random number falls in the cumulative distribution that tells you the next letter.
Yes.
Got it. All right. Thank you. That's what I thought, but I just wanted to make sure.
Yeah.
Sounds very much like a Monte Carlo approach.
Yeah. Well, most of the Bayesian computations are all done by Markov chain Monte Carlo methods, because they're independent of the number of parameters that you have to deal with.
You can use that approach in transport processes in physics, where you have certain probabilities of scattering or production or annihilation of particles, and you simply track each particle by a Monte Carlo process using these cumulative probabilities for each particular process it might encounter. Very
Right.
computer intensive, but it's sort of a you build up a distribution that way.
Yeah, no, this is exactly how it was done during the Manhattan Project. That's where this whole design started. And it was Ulam, a mathematician there, who designed this structure. Fermi took the ideas and actually physically implemented them with a mechanical device to move them around through a scale model of the pile that they were using, and designing, using it to calculate all of the transition probabilities and the number of neutrons going off and who were going to hit something else. All of that stuff was in the original. That was all came out of the Manhattan Project.
Yeah,
and it was basically Ulam and Fermi who worked at the Manhattan Project.
if I remember correctly, I think they were able to show that using plutonium, the so-called gun method would not work. It would fizzle. And that was kind of a crisis in the Manhattan Project at that point, because separating U-235 from U-238 would give you one bomb by 1945. You needed to design a bomb using plutonium, but plutonium was much more neutron reactive than uranium. So when you started to assemble a plutonium critical mass, it would start to react before it got fully assembled and just fizzle apart. They had to completely redesign the triggering mechanism for the bomb as a consequence.
Yeah, I can't remember who was the engineer who figured that out for them.
I think it was oh God, the Pizzioli, Italian. Anyway.
Yeah, I used to know it, but I don't know it anymore. Yeah, it was that all of this work initiated at the Manhattan Project for doing all of the scattering in various parts of the pile. So yeah, this is that was the and that was called the Metropolis method, I believe, at the time.
Yeah, sounds right.
Yeah. So if you're interested in the history of this, look up the Manhattan Project. Ulam made a great book. What's it called? Hang on. Let me look in my library. What's it called? Adventures of a Mathematician. That's what it's called. Adventures of a Mathematician. And it's a really interesting read. I would strongly suggest that you read that in here. Okay, further questions?
Well, thank you. I thought that was very interesting.
Okay, yeah, this was supposed to be just material that I sent out, and then I just, as you saw, I was still typing when when you got here, and finally.
Now, this was a great diversion. I think this helps give some insight into where we've been and where we're going.
Yeah, that was the reason I wanted to add it, was because I thought we could use a better understanding of how channels actually work and how the probabilities of all of these various objects occur and how they're built. So obviously you have to do uh, in order to get for a large collection of English in a corpus or in a source, you need to do the appropriate transitions here in a discrete Markov model, and you then work the entropies on the probabilities by repeatedly doing it and finding the averages. So anyway, yeah, this is a way to understand a little bit better about how all of this actually works and how all of the everybody always starts with the postulate of equal probability, and it's a very bad approximation, except in some occurrences, and but it was the basis of Boltzmann's work, of Maxwell's work. So I felt that in order to understand better how it really works, we needed to understand a little better about how all of the various structures that are really used, as opposed to that very crude equal a priori probability postulate.
Is there a relation here to how the neural systems, how the human neural systems then process words?
There is, but it's a different structure. This, at least I should say, it depends upon the model you're using. For the connectionist model of the brain, they're similar, very similar to this kind of structure. But there are other structures for models for the brain that are not. So, but if you want to take a look into the connectionist model of the brain, this will give you a similar kind of structure.
Thank you.
I can see how a software program like Dragon, a dictation program, or dictating into your cell phone, for example, you can watch as it self-corrects, as it's attempting to make sense of what you're dictating. And so, it's obviously got a huge body of the English language as part of the program, and attempting to see what makes sense. I'm just thinking that something like poetry, dictating poetry into such a program would be very difficult for it because it doesn't use English in the normal fashion.
Well, that's true, but there's actually various kinds of poetry robots on the web. You ought to go search in Google for poetry robots, or what are they, bots, and find the websites that have them and take a look and tell me what you think of how they compare. But people have looked at that structure as well. I haven't looked into it, so I don't really know how well or good they are. But I do know they exist and that people have studied them a lot.
Interesting.
Yeah. Okay.
Are we to assume you're going to send out is this in LaTeX? What kind of a process do you use to type? What's the word process you use?
LaTeX.
It is LaTeX. Okay, to get the symbols in. But can you send us a PDF or post that, or?
Yeah, I will. I just again, my my problem with posting this stuff so far this week has been that
Oh, no hurry, no hurry. No excuses. You have absolutely no excuses to be made for anything that you do for us. It is just amazing. Thank you.
Well, yeah, it always seems to take at least 2 or 3 times as much time as I think it's going to take to do. I have no idea why, but it seems to be that way.
A priori, you're optimistic.
Yeah. And it was funny. I used to have a rule whenever I was estimating as a consultant, and I never use it myself, unfortunately. But it would really. I'm sorry, I got to cut that off. The rule that I used to use for figuring out how long a consultation would take would be I'd figure out what I thought it was. So let's say I said it was going to be 2 weeks of work. So the first thing I would do would be change the unit to the next higher. So hours went to days, days went to weeks, weeks went to months, months went to years. So if I had said it was 2 weeks, then I would first take it by 2 months, and then just to be safe, I'd multiply by pi. So it would be 6.2 months as the estimate if I thought it was going to take 2 weeks. And that usually worked pretty well. And I don't know why I ever stopped using it, but I unfortunately always base my work on what I think it's going to be instead of using my own rule for how to figure it out.
I love that one. That's great. Unless I was paying the bill.
I love multiplying by pi. That's hysterical.
Well, I am a mathematician. I mean, you gotta do something. I'm sure an engineer would just use multiply by 3, but
no, I would have been dumb enough to just say 2 weeks or 2 days or what it was, and then I would have worked for 3 months.
Yeah. Anyway, so I will correct the typos in here, and I will send it out. And I'm assuming there's no more information. I'm going to stop the recording.